Hello, I am Maxime Lafond from the Lab in Lyon, and today I'm going to work about shear wave passive elastography for crystalline lens elasticity measurement in the context of our work on presbyopia reversal using ultrasonic cavitation. Here on the left is an image of an adult crystalline lens. If you could look inside, you would see disulfide bonds forming between proteins and fibrous cells aggregating, reducing the microcirculation of water and micronutrients. From the age of 45, the lens would get stiffer, preventing near vision. This is presbyopia. Presbyopia affects virtually every adult past 45 years old and really impacts quality of life. Today, there is no real treatment of the cause of presbyopia, but only various ways of correcting for it, such as spectacles or with increasing aggressiveness, surgery. What we propose is to use ultrasonic cavitation to interact with the lens structure and restore its flexibility. Here, what we got with our first trial, and I want to show that because you can see that huge cataract that was formed in the middle of the lens. This is formed because of energy deposition and really highlights the fact that we need to produce cavitation without heating, and safety is, of course, paramount in that application. The approach we are proposing is to determine the cavitation threshold and produce cavitation into the lens, then assessing transparency and looking at microscopic changes in histology, and finally use shear wave elastography to monitor the changes in stiffness. So here is our experimental setup. You can see our ultrasound treatment device is composed of 4 confocal transducers with an imaging array in the middle. And here we can place a pig eye and place the focus of those 4 transducers in the crystalline lens. We have a Cantel medical ultrasound probe at the top for placing the focal spot in the lens, and we have another ultrasound array at the bottom that's connected to a Versonix, and we can extract the received data to perform beamforming and passive cavitation imaging. And what we did is that we summed the PCI pixel values inside the lens and were able to extract a cavitation threshold from that information. And you can see that cavitation was produced. We reached the plateau at the high end of our amplifier, which was about 2 kilowatts with relatively short pulses of only 60 cycles. So here is what we get. So we can clearly see that cavitation cloud that was formed in the middle of the lens. Something we could observe is that, so here we can see the anterior and posterior edges of the lens, but inside those white spots are artifact, but there's only actually no speckle at all. Here on the right, we can see another example with an older pig, and in that case, we can actually see the cavitation cloud that was formed in the middle and then kind of propagate to an outer layer. Here are transparency images. Shown on the left, it's our positive control where we deliberately exposed the lens to ultrasound for 30 seconds, and we could see, for example, residual bubbles. We could also see that the lens lost in transparency and appears a little bit milky. That was actually different from the first image I showed with the cataract, because cataract is very opaque, but this one was more milky, and it's more like mechanical damages that are changing the way light is propagating through the lens. With only 10 seconds cavitation, though, no change in transparency was observed. On histology, we can clearly see the mechanical damages in our positive control, with also the blueprints of residual bubbles. Here on the top right is the negative control that was not exposed to any ultrasound. And on the bottom right is the image with only 10 seconds of cavitation, and we could see no evident differences between the control and the cavitation sample. For elastography, we take a sample holder that was made from agar gel, and we place gelatin beads or the lens in the center and make it vibrate with a function generator and amplifier. We placed an imaging array on top, and then we follow the displacement of the waves at the surface of the lens or the gelatin bead. By doing so, we can track shear waves propagating at the surface, like in this example where we can see 2 consecutive frames and can clearly see the displacement. The idea is to track those displacements for different frequencies from 0.5 to 3.5 kilohertz, assuming that as a function of frequency, those shear waves at the surface contains information on what's happening in deep layers. Here are dispersion results. In blue, the wavelengths as a function of frequency, and in orange, the speed of the shear waves as a function of frequency. On the top right here is the result for gelatin beads, and the bottom right is the result for the lens. If we average the obtained value between 1 and 2 kilohertz, we can find values that are actually very close from the literature values. For the porcine lens, were slightly higher, but this value was obtained with an assumption of on the frequency of an apparatus, which might be inaccurate. So as a conclusion, we show the cavitation threshold observed with passive cavitation imaging and use that in ex vivo lenses. We observed that limited time exposure resulted in no observable damages. Perspectives to the studies are to observe the ultrasound interactions using histochemistry, as well as to evaluate the stiffness modulation using the shear wave elastography that was developed in this project. Thank you for your attention.